Okay, so hi all, good evening and welcome back to the fifth week of live sessions for AI SMPS. So this week we are having this session on Friday instead of Monday because of some unavoidable circumstances, but from next week onwards we'll be having the session on Monday itself. So just clarifying that at the same time at 6 p.m. So yeah, let's get started with today's session. Today we'll be discussing some questions from branch and bound and A-star algorithm. So before we get started, is there anything specific that you would like to discuss? Okay, if not, then cool. Then let's get started with the first question. Okay, so here you see a map. The circles represent the nodes and the edges connecting them have some weights, which is the distance between those nodes. And there are some edges that are not being shown in the graph here, and you can assume that they have a very huge cost or a very huge distance. Okay, and we call them the infinite cost edges. What you have to do is we have to apply the branch and bound algorithm, which will start looking for a TSP tour, and while doing that we have to find the lower bound on the cost of the tour that it will begin with. Okay, so you might have come across this in the lecture videos. um, I'll give you a couple of minutes to try to solve this, and then we can discuss the solution. To address the question, no, not today. We are not going to discuss week 6 problems today. We'll discuss them on Monday, okay, at our usual time. Today we'll just cover some week 5 questions. Just a compensatory class for Monday, this week's Monday. Okay, I think week 5 deadline might have passed already, so this might just be a revision for you guys. But yeah, I hope that helps. So yeah, I'll give you a couple of minutes and then we can discuss the solution. Okay, does anyone have a solution or an approach on how to solve this? Okay, let's have a look at the solution and hopefully that will help you remember. So this is the map that we had, right? So we have named the nodes starting from A, B, C, D and up to I. Okay, or yeah, alphabetically, and each of these distances that we have put them in a tabular manner in this distance matrix over here. Okay, so what this basically tells us is the cost of going from a node to another node. Okay, so the cost of going from A to A is 0, that of A to B is 12, okay, and so on and so forth. Okay, so this is known to us, and when we have to find the lower bound, what we do is we look for the two minimum most costs in each row. Okay, so for the first row, which is all the distances we could go to from A, 12 and 14 are the lowermost two lowest most costs, okay, which correspond to the edges AB and AC, right? And so we add them up and we write that over here, okay, and we repeat this process for each of the rows. Okay, so for B, the two lowest costs are 12 and 10, which sums up to 22, corresponding to edges AB and BC. Okay, so we again write those down, and we do this for all the rows from A, B, C, D up to I. Okay, so we get a list of these minimum two edges in each of the rows. So what we'll do is we'll sum these up and then divide it by 2, because if you think about it, we are counting each edge twice, right? So we have to divide the sum by 2, and that will give us the lower bound. I hope that was clear. Any doubts in this question? Okay, if not, then great. And let's go back to our questions and check the solution. So as we see, it is actually 108, which is what we also got. So that makes it clear. So this was the lower bound, okay, and remember that this may not result in a valid tour. Okay, this is just a lower bound that we are estimating. The next question asks us to find an optimal tour now. For the same graph and the same distances given to us, we have to find the actual optimal tour, the TSP tour that we will be taking. Okay, you can consider starting from any of these nodes or any of these cities, and you have to maintain the conditions of a traveling salesman problem and come up with the actual optimal tour. Okay, so again I'll give you a couple of minutes, try to solve this, and then we'll discuss the solution. Okay, so any solutions or partial solutions? Okay, so this is a small graph. Okay, so here we can actually try to find the optimal tour by hand itself. Sorry, let's say we start from this node A. Okay, and let's see which direction can we take. So here it seems that we can go to B with distance 12, to C with distance 14, and I with distance 55. And B looks most promising, right? So we'll choose to go in this direction and cover A to B, and then we'll be at P. Now we have only one option to go, to C with cost 10. That's what we'll do. Then from C, which direction should we take? D, that's right. Although 14 looks more promising, but if we go up to follow that particular path, we'll end up in a cycle, right? And we have to avoid that. So we'll take the path to D with cost 77. And then once we are at D, which direction should we take? E, that's right. Here again, if although 10 looks the most promising, but the issue is if we follow 10 and go to F, then we could go to either G and E. And if we go to G, we won't be able to come back and cover E. And if we go to E, we'll end up forming a cycle again, right? So from D we have to follow this path and go to E, followed by 12 and go to F. Then we go to G, H, I, and then back to A, and this completes our tour. Okay, and if we just sum up all the path edges that we encountered and report their total sum, that will give us the optimal cost of the optimal tour. Okay, so this is essentially what we did. Okay, if you sum up all these, we'll get 296 as the optimal cost. Let's check our solution, and it is 296. So any doubts in this question? Okay, that's great then. Then let's move on to the next question, which will be branch and bound and A star. Okay, so we'll be using the same graph, the same map for both branch and bound as well as A star problems, and we'll only be discussing the plain A star method, not the variants of A star. But once you understand A star, all the variants of A star method should be easily adaptable to. Okay, so first things first, so our goal is still the same. We have to start from the S node and we have to reach the goal node, which is indicated by G. And these costs that you see on each of the edges, these are not heuristic values, these are actual costs of going from one node to the other. Okay, so if you think about this, consider S to K. Okay, if you have to follow the Manhattan distance heuristic that we looked at in the previous live session, the cost would be 40, right? Assuming that each small box over here is 10 cross 10 units. Okay, so we have to cover 1, 2, 3 and 4 boxes, so it will be 40 units, right? But here the cost given is 60, which is the actual cost of going from S to K. Okay, so don't confuse this actual cost with the heuristic cost. We'll still be using the Manhattan heuristic value, but that will come later on. Okay, so these are the few starter points. What we have to do in the next question is apply branch and bound. Okay, some other information that might be useful to you is that each of these small blocks is 10 cross 10 units in size. Okay, if several nodes have the same cost at any particular point in the algorithm, we have to break the tie using alphabetical order. of the nodes. And if the same node occurs multiple times with the same cost, then we have to use the open sequence number to break ties. Okay, or in other words, we have to refine the one or explore the node that occurs that was placed the earliest in the open list. Okay, and wherever necessary we can use the Manhattan distance. So all these might seem a lot of instructions at this point of time, but it will get clearer as we solve the problem. So first we have to use the BNB1 or simple branch and bound algorithm, and in this variant of branch and bound we allow cyclic refinements. That is, once you start from a given node, you are allowed to revisit that node later on in your search tree. Okay, so try to solve this using BNB1, and we have to report the 5 nodes, which is from 6th to the 10th nodes that were refined or explored by this version of the method. So I'll give you maybe 2-3 minutes to try to solve this, and then we can look at the solution. Please let me know if you come up with any partial solutions till then or any doubts in the question. I'll finish this thing and I'll upload tomorrow. Okay, tomorrow will you come to lab? Okay, come in the daytime maybe, because evening we might not be here. Okay, any partial solutions or doubts in the question? Okay, let's try to solve the problem and hopefully that will resolve any doubts if there are. Okay, so we'll do one thing. We'll use a particular uh, format to solve this problem. Okay, we'll use this box. Okay, there'll be three elements in this box. Okay, the first would be the name of the node that we are currently at, or we are refining or exploring. The second would be the order number in which this node was visited or refined or explored, and then the last entry would be the cost of going from the start node to this node. Okay, so it makes sense that the cost of going from start node to itself would be 0, right? And remember, by here and by cost here I mean the actual cost. Okay, so the first node would be node S, which was visited first and has cost 0. Okay, now which are the nodes that we could go to from S, right? They are E, J, K and O, right? So let's write that down. We have E with cost 40. Okay, so we have E with cost 40. We have J with cost 30. We have K with cost 60 and O with cost 60. Okay, now which of these nodes do you think we'll be visiting next? J. That's right, thanks for answering. So J looks the most promising, right? So we'll be visiting J next. Let's label this as order number 2, and now let's look at what are the nodes we could go to from J. So we are at J, right? Or hypothetically think that we are at J. We could go to N with cost 40, we could go to A with cost 60, and we could go to S back again with cost 30, right? So let's write that down. So from J we could go to N. So remember, the cost of going from J to N is 40. So the cost of going from S to J to N would be 70, right? 30 plus 40. Another node we could go to is A, and the cost of going from J to A is 60. So the cost of going from S to J to A would be 60 plus 30, which is 90. And we could go back to S. Okay, so this is what we mean by cyclic refinement being allowed. Okay, so we could go back from S to J to S again, and the cost would be 60. Okay, so let's mark the nodes that we have already visited with a green color so that we know. Okay, now from among all the nodes that don't have green color or that we have not yet visited, we will be choosing from all the nodes that are available to us. So that includes E, N, A, S, K and O. So out of these, which one do you think will be followed next or explored next? E. That's right. That's correct. So E will be explored next, and we will assign it order number 3, and we will keep on expanding in a similar fashion, okay, until we find the complete search tree, or until we reach a stage where we can answer a particular question that has been asked to us. So let's go to the full search tree that I have and try to see if it's correct. Okay, so we were at S, then we added E, J, K and O, right? From J we added A and N, S, right? And then we explored E next. Okay, so remember this one written over here at the top along with the alphabet, which is the node name, tells us the order in which they were visited, right? So S was visited first, J was visited next, E was visited third. Okay, and similarly if we keep on expanding, okay, we would reach a particular stage where K was expanded next, then O was expanded. Okay, and we will keep following this particular fashion until we reach a state where we can answer the question that has been asked to us, which is to report the nodes numbers 6th to 10th that were visited by our branch and bound version 1 method. Okay, so that would be in our case S. Okay, this particular S, remember this S is different from this S and this S. Okay, this particular S occurs at the beginning. This S occurs in the path or the partial path from S to J to S, and this occurs in the path from S to E to S. Okay, so all these S's are different. So the 6th node that we visited would be S, 7th would be N, 8th would be again S, 9th would be A, and 10th would be J, right? So if we go back to the solution, the 5 nodes from 6th to 10th nodes refined or visited or explored by branch and bound version 1 would be S N S A J. Okay, so this is the answer. I'll go back to the search tree once. I'll leave it on here for some time so that you can convince yourselves of the solution, and then we'll move on to the next question. If there are any doubts in this question, please feel free to let me know. Sure, we will come to BNB2 next immediately after this. So in BNB1, if you remember, we allowed cyclic refinements, right? So we could go from S to J back to S, right? So this is what we mean by cyclic refinements. In BNB version 2, we won't be allowing that. Okay, so in that case we will not be able to go from J to S again. Okay, that will be the difference between BNB1 and BNB2, but we'll come to that. Why E? Okay, the reason why we visited E third is because at that stage okay, so we were at this point, right, when we decided to visit E. At this stage the options available to us are E, N, A, S, K and O, and out of all of these, this has the lowest cost, right, 40. All others have higher costs. That's why we visited E after exploring this J node. Okay, so at any stage we have to choose the best looking node from all the options available towards us at all the depths of the search tree. Okay, that's why we chose E. And there was a question about tie break, so let's go back to so these are the different instructions given to us. We have to use alphabetical order to break ties. Okay, if the same node occurs multiple times with the same cost in the open list, then we have to choose the one or refine the one that has been there from a longer period of time in the open list. Okay, I think this will be of more importance when we look at the A star node, but for the alphabetical one we could look at a simple example in this branch and bound method itself. So at this point, after visiting E, right, we would have the option to choose from all the different nodes which are A, B, F and S. Okay, the children of J, which is A and then S, and uh, K and O. So of all of these, we will see that S, K and O, all three of them have cost 60. Okay, but which of them occurs first in alphabetical order? K, right? So we will visit K after E, followed by O, followed by S. Okay, so this is one example of how we break ties. Okay, so I hope that helps with the doubts. Any other doubts in this question? Okay, if not, then that's great. Let's move on to our next question then, which is the same graph, same map, but the method changes. Okay, so in this one we chose BNB1, branch and bound version 1, where we allowed cyclic refinements. Okay, so paths like SC, 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 where nodes are allowed to be repeated. Next we are going to okay, so this was just another part of the previous question where we had to list the costs associated with the nodes that we entered, and you can verify that later on that it's 60, 70, 80, 90, 90. Okay, the next method that we are going to use is BNB2. Okay, here we prevent cyclic expansions. Okay, so a node once visited is not allowed to be visited again in the partial path. Okay, so everything else remains the same, just that we are not allowed to do cyclic refinements. So I'll leave this on here for maybe 2-3 minutes, and I'll let you try to draw the search tree and find the solution, and then we can have a discussion on the correct solution. Okay. Okay, so we already have a couple of solutions in the chat box. That's great. Let's have a look at our solution and see if we reach the correct solution. Okay, so like in the previous case, we will try to draw a search tree. Okay, so we will start with S again, 0, and visited first. We will have E with cost 40, J with cost 30, and K and O with cost 60 each. Okay, so till now our search trees are exactly the same. Again we will choose J next. Okay, but when we expand J, in this case we won't allow another S. We will only allow N, which would have cost 70, and A, which would have cost 90. Okay, no addition of S will be there because we are preventing cyclic refinements. Okay, if this is clear, let's look at the full search tree. Okay, so we started with S. Okay, we added the 4 children of S, or 4 nodes we could go to from S, which is E, J, K and O. Okay, now out of all of these, J looked most promising, so we expanded J without S. Okay, so that gave us A and N. Now out of E, A, N, K and O, E looks most promising, right? So we expand E next, again without cyclic refinement, so we have only A, B and F. Okay, so again if we keep doing this, keep following the similar pattern of propagating our search tree or expanding upon our search tree, then we will reach a stage where we will be able to answer the question that has been asked to us, or we will reach the goal node depending on till how much depth we want to go in our search tree. So again we have to look at the 6th to 10th nodes that we refined or visited, right? So here we start with N, right, which is the 6th node, then A, then F, okay, then N again, and 10 would be L. Okay, again remember the difference. There can be multiple occurrences in a particular partial path, across different partial paths. Okay, so this N is different from this N. Okay, and because this N is coming from S to J to N. Okay, whereas this N is coming from S to O to N. Okay, so these are all different N's. So the answer in our case would be NAF and L. Okay, I'll go back, maybe zoom out a bit, and I'll leave this here for you to convince yourselves that the solution is correct. Okay, if there are any doubts, please feel free to let me know. After this we'll go to the A star method, but that will be after maybe 2 minutes. I'll just leave this on here for a while so that you can get comfortable with the solution. Okay, so yeah, I had just gone to get some water. I'm back now. So there are a couple of questions in the chat box. Why F is the 8th node and why not N? Okay, let's have a look. Okay, so before we explore F, we would have explored 7th, which would be A, right? So the options that we would be looking at are A, B, and F, B and E, then O, T, U, C, and E. Okay, no, only O, T, and U. Then F, H, L, Q, and we would have N, Q, and U. Okay, so N and F both have cost 100. So we are choosing F because F is occurring alphabetically before N, right? That's the reason. And the second is, kindly add the edge cost in the figure. Which figure are you referring to, Satish? In the search tree? In the search tree we already have the costs. Okay, so the third element over here is this 30, 90. These are all the costs associated with the partial paths. Okay, so 70 is the cost of going from S to J to N. Okay, this whole partial path. 120 is the cost of going from S to J to N to T. Does that address your doubt? Okay, I hope it does. If not, please feel free to let me know. Okay, any other doubts in this question? If not, then we can move on to the next method that we are going to have a look at, which is the A star method. Okay, so we looked at branch and bound version 1, version 2, and next we will look at A star. Okay, so I'll just give some intuition behind A star. So the difference, there are two major differences between branch and bound and A star, or the method that you've seen till now, and A star. One is that till now we use the actual costs, right? Now we will also be using the Manhattan distance as a heuristic. Okay, so let's say we are starting from this particular node. Okay, let's say this is our start node. We do some explorations and we reach a particular partial path to our core node. Okay, so this is a partial path that we have obtained, and let's draw a line to demarcate this is a partial path. We are yet to reach our goal state, okay, which is somewhere over here. So because we have already found a partial path, we would know the actual cost of going from S to this intermediate node. Let's call that G. Okay, and then we would use a heuristic like Manhattan distance to estimate the possible cost of going from this intermediate node to G. Let's call this H. So we will define a function f equals G plus H. Okay, and we will be using this cost to build our A star search tree. Okay, another major difference is the concept of propagation improvement. Okay, so suppose we are building a search tree. Let's say we started with S, then we could go to another child here, another child here. Let's say the cost of going to this particular child is X. Okay, let's give it some value. Let's say X is 50. Okay, and let's say the cost of going to this particular child is 100, and the cost of going to this particular child is let's say 52. Okay, So in the first scanning, we would think that this is the next node that we are going to explore. Okay. um, or actually, let's name these nodes so that it becomes easy for us to understand. Okay, let's name this as A, this as B, and this as C. Okay, and let's say this has cost 40 instead of 52. Okay, now we will think that C is the most likely node that we are going to explore next. Let's say we go to C, we explore C. Okay, and we find some path. Okay, there might be intermediate nodes in this path. Okay, to go back to A with a cost, let's say 48. Okay, so by following this partial path, we have found a path from S to A that is a lower cost than this path. Okay, so what we will do is, in our search tree, we will block this particular partial path and say that since we have already found a more optimal path from S to A, this particular path is no longer worth exploring. Okay, so we will cross this out and we call this as propagation improvement. Okay, it might seem a bit fuzzy over here, but it will get clearer as we look at the solution. Okay, yeah, was there a doubt? Okay, I guess not. Okay, so let's try to solve this. So again, we can start building sorry, we can start building the search tree. So we will start with our S. Again, this is the first node that we visited or refined, and the cost here, remember, would be G plus H. Okay, so G in this case is the actual cost of going from S to this node, which will be 0, right? But H is the heuristic cost of going from, heuristic cost associated with this node, right? And what would that be? If you recall from the previous lectures, we use the same graph, right? So how many hops do we have to go from S to G? Okay, that is 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15, right? Or is it 16? Can someone just confirm whether it's okay? It's 16. Okay, so multiplied by 10, that would be 160, because we assume that each of the boxes are 10 units cross 10 units. So our cost would be 160 instead of 0. Okay, so when we expand this to E, J, K and O, we have to remember that. Okay, so for E we would have, what would be G? G would be 40 plus the Manhattan distance or a heuristic value for node E. Okay, so can someone quickly compute that and tell me what it is, what it would be? For nodes E, J, K and O. Okay, 170 for E. Let's write that down. Okay, what about J? 190 for J. Okay. What about K and O? K is 130. Okay. What about O? Okay, we have conflicting answers for K. Let's verify it. So we actually have the tree constructed. Okay, I suppose you all were telling me just the heuristic value, right? Not the total cost. So this would have been 170 plus 40, right? So 210. Remember, we have to add G plus H, right? So the cost of E would be 210. And J would be 190 plus 30, which is 220. K would be 130 plus 50, right? Was it 50? No, K was 60. So that should have been 120, right? They should have been 120 plus 60 would give it 180, and so on and so forth. Okay, so this is what your search tree would look like. Okay, at least the first stage of the search tree. Okay, look at this only till, sorry about that. Okay, look at only till this line. Okay, so I hope it's clear until this point. If there are any doubts, please let me know before we proceed with the rest of the method. Okay, I hope this is clear until this point. So again, we will follow the same process. Okay, now that we have S, we have explored S already, right? We have to choose from E, J, K and O. Yes, we just figured. So E has 170, but we also have to add the actual cost of going from S to E, right? Which is 40. So the total cost becomes 170 plus 40, which is 210, right? That's how we got these costs of 220 and 180 and 180 for J, K and O respectively. Okay, so there's a doubt on whether it is 170. Let's look at E. So what is the heuristic value for E? Okay, how many boxes do we have to cover? So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, or 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, right? 17 boxes we have to cover to go from E to G, right? And each of the small boxes 10 cross 10 units. So 170 is the Manhattan distance of E. That's how 170. Okay. Okay then. So from these E, J, K, O, which one should we choose? K, right? Because K has the lowest cost, and also although K and O have the same cost, K comes alphabetically before O, right? So next we will expand or refine K. Okay, so once we refine k, we will add f, h, l and q to the search tree. Okay, again remember, when we are adding f, we will add the actual cost plus the heuristic value. Okay, so the actual cost of going from s to k to f would be how much? The actual cost of going from s to k would be 60, plus f would be 60 plus 40, which is 100. Okay, so this would be our g. What would be h? Would be the heuristic value of f, which is Manhattan distance of f to g. Okay, so that would be 1 plus 2 plus 3 4 5 6 7 8 9 10 11 12 13 14 15. Okay, so 150 plus 100 gives us 250. Okay, that's how we got a value of 250 for f. Okay, similarly for h, l and q. For now, ignore these cross marks, we will come to that. Okay, so once we have explored k, the available options to us would be E, J, F, H, L, Q and O. Out of these, which one will we explore next? It will be O, right? See, L seemed 190, but we already had O with cost 180, right? So we will explore O first. Yeah, so we'll explore O next, and we will add N, Q and U to the search tree. Okay, after O, we will explore which node? Then we will explore L. Okay, because it has cost 190, and once we explore L, we will add H again to the search tree with cost 260. Now notice here, at this stage our method realizes that we have found path from S to H via SKLH with cost 260. We already had a path from S to H in the search tree, which is S to K to H directly with cost 270. Now that we have already encountered a path with lower cost from S to H, we will put a cross mark over here, meaning that this particular partial path from S to K to H is no longer worth exploring. Okay, so in the later stages, we will not propagate H, and we will not consider this as a potential candidate that we would look to refine in the next iteration or the next step of the algorithm. Okay, so I hope this is an example of propagation improvement that was clear, that was put in the solution. And if you keep expanding the solution, you will find several other instances of Rishabh, can you please mute yourself? Thank you. Okay, so if you continue to explore the solution and build the search tree, you will see that you will find several instances where this propagation improvement is helping you out. Okay, so similarly, you will also cross out Q at some point, N at some point, and A at some point. Okay, so yeah, this is how you build a search tree for A star. Maybe I'll zoom in a bit, zoom out a bit, sorry, and I'll leave this on here for a while so that you can convince yourselves of the solution or the search tree. Okay, um, once you have convinced yourselves, we can discuss the solution to the question that we had, and if there are any doubts about any step that we used in this method till now, please feel free to let me know. Okay, I'll leave this on here for maybe a couple of minutes. Okay, so there's one more doubt about propagation improvement. Okay, let's go over that once more. So basically the idea is I'll parallelly draw as well so that it's easier. Okay, so we started with S. Okay, I'm not writing all the details of the nodes over here. Okay, after S we added E, J, K and O. Okay, so E, J, K and O. Okay, after we explored, let's mark the explored nodes with the green color. Okay, so we explored S. After S we explored K. Okay, number 2. Once we explored K, we added the nodes F. Okay, I'm no longer drawing the boxes. Okay, F, H, L and Q. Okay, which node did we explore next? The third node that we explored was O, right? So we explored O, and once we explored O, we added, there's no space here, but let me try to fit it in. We added H, Q and U. Okay, now now look at this tree over here. Okay, initially we had a path from S to K. Okay, S to K to Q, S to K to Q, that had a cost 210. Okay, but now we found one more path from S to O to Q with cost 200. Okay, which is lesser than 210. So our algorithm thinks that now that I already have a cost of 200 from for the path from S to O, okay, S to Q, sorry, S to Q through O, I no longer need to explore this particular path. Okay, because this had a cost of 210. So if we keep on exploring further via this path, the added cost will always be greater than the path that we will that greater than the cost that this particular path has to offer us. Okay, so we cross out this particular path. Okay, similarly, once we explore this L node, we found a path from S to H. Okay, this particular path. Okay, S to K to L to H, which had a cost 260, which was again lesser than the cost of this path. So we crossed this out as well. That is essentially what propagation improvement does. Once we encounter a particular partial path that is more promising than some previous path that we had already explored, it crosses out or cancels the previously explored path, which it knows is not going to give us optimal results. Okay, so that makes our algorithm more efficient. we, it prevents us from keeping on exploring unnecessary directions of search. Okay, okay, cool. Any other doubts in this search tree over here? Okay, thanks for confirming. If not, then that's great. Let's go back to the questions that we had. So the question told us determine the 5 nodes again from 6th to 10th nodes that were refined by A star. So if we go back to our search tree, the first node to be refined was S, followed by K, then O, then L, and finally Q. Now comes the 6th to 10th node. Okay, so the 6th node that was refined was E, followed by J, N, followed by R and then F. Okay, so our answer should be EJNRF. Let's have a look. And that is our answer, EJN, R and F. Okay, so this is an example of A star. A variant of A star is WA star, which you may or may not have come across, depending on which week is it covered in the course videos. So remember, in this particular version of A star, we gave equal importance to the actual cost as well as the heuristic cost. Okay, so we did F equals to G plus H, right, where G corresponded to the actual cost of the partial path and H corresponded to the estimated cost from the partial path to the goal node, right? Now what we can do is we can give different weights to each of these components. If we want to give more weightage to the actual cost, then we can add a constant over here or a scalar over here, W, that gives it some weightage as compared to H. Or if you want to give more weightage to H, we can add a scalar over here as well. Okay, that gives us a variant of H star algorithm. Okay, and everything else about the procedure remains the same. So you might come across this in the lecture videos, or you might already have come across it, in which case you would know what I'm talking about. Okay, that brings us to an end of the questions I had for week 5. Is there any other doubt that you had that you would like to discuss? Week 6 questions we'll cover in the coming week on Monday when we have the live session. Okay, so week 6 we can put on till we can postpone to Monday. If you have any specific queries you want to be discussed from week 6 on Monday, you can tell those to me right away. H star, can you elaborate on that? No, I was talking about A star, not H star. Is there any method named H star? I'm sorry, I'm a bit foggy about it. Okay. I think it was just my might not have pronounced it clearly. I was talking about A star. Okay, this one, A star, and the variant of A star is called WA star. Okay, anything specific that you would like to discuss today, or anything specific that you would like to have discussed on the coming Monday for week 6? Let me know. Okay, if not, you can also use the weekend to go through the week 6 materials and then post something in the discussion forum, although I would recommend you post it sooner than later. Okay, so that I am aware. Lecture example from RBFS. Okay, I'll make a note. I don't remember what RBFS is, but I'll find it out. So are you suggesting this for week 6 or today's live session? Okay, week 6. Okay, I'll make a note, RBFS. I'll see if I can add some questions from that. Okay. Anything else? If not, then I think we can close the session for today. Okay, it's an exercise problem given in the lecture video. Okay, I'll also go through it. Even I'm not, I don't think I remember it, but yeah, maybe once I go through the lecture videos or the slides, I'll remember what it was about. Okay, then week 5 assignment question 1. Okay, let's have a look at that. Which question over here? Question 3. Okay. Identify the second segment that will be used to refine S1. Okay. What is the estimated cost of S2 node? Okay, so I guess we have to solve this from the beginning, which will take some time. Is there any specific doubt you have in this step? Okay, no worries. You can also in the meantime post some partial. Okay, no worries, no worries. We can discuss this on Monday again. Or in the meantime, what you can also do is uh, work out the partial solution that you have, and then post it in the discussion forum as well. Okay, so then I'll also be able to have a look at the partial solution that you have. Bhaskaran sir, who is the main TA, he will also be able to have a look and help you out, and then we can work through where exactly the problem is occurring. Okay. Cool then. Um, Thank you. Thanks all for attending. And yeah, let's meet next Monday. Yes, by forum I refer to the discussion forum available on Swayam portal. Okay. So, okay, there is a doubt. Please feel free to go ahead. Jayan, can you hear me? What is the difference between S1 and its child node S2? So if you refer back to one of the examples that was covered in the lecture videos, right, we were trying to add construct a tree by adding and not adding a particular edge to our tour, right? Remember one of the lecture videos when we were discussing the TSP problem, we used to add a particular edge to our graph, okay, and then we used to add another edge, another particular configuration of the graph without that edge, right? That would be not S2. So I think that is the difference that is occurring over there. uh, See, we have S1 and not S1, S2 and not S2, S3 and not S3, so that is the difference. Okay, but what exactly will those be, that we'll have to figure out using the distance matrix given to us and the other information. But yeah, I would encourage you to try to explore um, what exactly that is. Like one of your friends also pointed out, try to post your that's what I'm saying, that we'll have to figure out from the distance matrix, right? And I'll encourage you to try to come up with a partial solution so that we can refine that solution from there onwards. Okay. Okay. Okay, then let's go close the session for today and meet on Monday. Okay. Have a good rest of the evening.